In the former class, we had learned thread. The thread, you can see in former class we can learn the thread example. Let's see. You are implementing Chrome. Chrome is one of Internet Explorer. Chrome is from Google. Is from Google company. Google company has famous. Google company is famous, and it has strong technologies.
Yeah.
So, but in China, Google's technologies, we feel is rejected and
unsecured.
Restricted. Yeah. So our feeling is the technologies of Google is less than the technologies of Baidu. Yeah, in China, Baidu is famous than Google.
Yeah.
If we want use Google software, we must use some
VPN.
Yeah, use some
proxy.
Plugin. We must use some methods to access the Google software. So it is not useful, and it's some business in China. So Google try, but in Europe, in America, Google has many users. Facebook in China, you can see less users. All of people in China use QQ and WeChat.
Forever.
Yeah. So Facebook has less users. Yeah. Okay. You want a page for each web page you open, so you can see the table. The crime has several pages. One page is one thread. So some pages are some threads. So you can see actually authors use separate processes for each page for a variety of reasons, including performance and security. Yeah, this is some example. Multi-threading processors is modern technology in current CPU. Multi-threading is meaning multi-process thread can be run at the same time. Yeah. So you can find the basic idea is processor resources are expensive and should not be left idle. So we want processor resources are useful at the same time. In all time, we want the resources can be used. So long memory latency to memory on cache miss. Hardware switches thread to bring in other useful work where waiting for cache miss. Cost of thread context switch must be much less than cache miss latency. Okay, this is hardware support for multi-threading. This is multi-threading, the image. In the left section, this is in processor. So you can find PC0, PC1. In the processor, this has multi-threading. And the memory is shared. Yeah, the main memory is shared. And the input and output, the I/O memory interfaces is for some memory. Two copies of PC and the registers inside processor hardware and looks like two processors, two software, hardware thread 1, thread 0, hardware thread 1. So you can see thread 1 and thread 0 is for PC 0 and PC 1. So multi-thread is useful technology. So if you you see in our universities, several buildings have several classes at the same time. This is like multi-threading, especially at the start point of semester. This week is number 15. Yeah. So many courses are ending. Yeah. So you can see in some buildings, some classrooms is empty. Yeah. But at the start point of semester, it is full. Yeah. The classroom is full. So in the university, the course have some times at the end of semester we find examination and study by yourself. So this is the condition for university. In the low level school, for example, 高中、初中、小学, yeah. In the low level school, you can see my daughter is 8 level. Yeah. So he must go to school in 7:30. He go home about 6:20. So all of the day he is in school. Yeah. So it's different. It's different from university and low level school in China. Okay, multi-threading vs multi-core. This is two technologies. Multi-threading and multi-core. You can see multi-threading can become better utilization. Multi-threading can become better utilization. You can see more hardware, better performance. This is, you can see, we can use a little more hardware to become 1.3 multiple better performance. So multi-threading can share integer adders, floating point adders, cache, memory controller. So this is good technology. Multi-core is duplicate processors. Duplicate is duplicate and is one by one. Yeah, duplicate. So you can see we can use 50% more hardware and can achieve two multiple better performance. Multi-core can share some cache memory controller. Modern machines do both multiple core with multiple thread per core. This is two technologies. We like multi-threading in current CPU. Multi-core can achieve better performance in the future. For example, in the future, the cost of multi-core is low and low. So multi-core can become popular and popular. The desktop computer, this is some performance change. You can see this is 4 cores, each capable of 2 threads. So we can see 4 multiple 2 equals 8 processors. Yeah, this is some i7-7700 CPU. The frequency is 3.6 GHz. Yeah, this is some CPU trend. Okay, this is some developer board. You can see this is some developing or developed board for developer. This is your course has embedding system. Yeah. So this is for embedding system developer board. This is the symbol Raspberry Pi board. This has quad-core processor. This has three-way superscalar pipeline. This developed board has level 1 and level 2 cache, but the level 1 cache and the level 2 cache, the size of cache is small. Level 1, the size is 32 KB. Level 2 has 512 KB. RAM is 124 GB. So this is literally all computers are doing parallel these days. Okay, this is for multi-threading, multi-processing, multi-threading. We like multi-threading better. Okay, parallelism challenges. We can see challenges to parallelism. Parallelism is great. What can do so many things, but what's the downside? This is two problems. One is how much speed up can we get from it? Two is how hard is it to write parallel programs? So this is some speed up example. Imagine a program that takes 100 seconds to run, 92 seconds in the blue part, 5 seconds in the green part. This is some speed up. Okay, this is the next image. You can see speed up with improvement equals execution time without improvement. Divide execution time with improvement. So you can see when I become 2 seconds to 2.5 seconds, when I become 5 seconds to 1 second, you can see the speed up is 1.02 1.026, 1.042, 1.053. Okay, this is Amanda law. This is the speed up, the calculation of speed up. Okay, this is some this is equivalent to prior inclusion. This is non-speed up part. This is speed up part. Okay, this is the trend of heart-breaking law. Heart-breaking is Amanda law. The amount of speed up that can be achieved through parallelism is limited by the non-parallel portion of your program. This is the trend of parallel portion. Okay. This is some example for parallel speed up. Speed up with enhancement equal 1 divide this equation. Consider an enhancement which runs 20 times faster, but which is only usable 15% of the time. Speed up equal, we can see this is 1.166. Amanda laws tell us that to achieve linear speed up with more processors, none of the original computation can be scaled. To get a speed up of 90 from 100 processors, the percentage of the original program that could be scaled up would have to be 0.1% or less. Okay, I'm sorry. Please take a rest. Yeah. 5 minutes. Okay, continue. Okay, we can see this is the second section of data races. Yeah, the data races is the thread gathering. Thread gathering is not deterministic. There is no guarantee that any thread will go first or last or not be interrupted at any point. If a different thread writes to the same variable, the final value of the variable is also non-deterministic. This is data race. Avoid incorrect results by one is not writing to the same memory address, two is cyclonizing, writing and reading to get deterministic behavior. This is some example, one example, sum reduction. We can see some 100,000 numbers on 100 processors. Each processor has ID. PN is from 0 to 99. Partition 1,000 numbers per processor. You can see some steps. Step 1, initial summation on each processor. So this is the for loop. Then you can see in the for loop, no data dependencies so far, not writing to the same address in memory. Step 2 is now need to add these partial sums. Reduction is divide and conquer approach to sum. Half the processors add pairs, then quarters. Data dependencies need to synchronize between reduction steps. This is the sum reduction with 10 processors. You can see sum has some processors. This is an example of sum reduction path to code. Path to code is, you can see, is from this. We can describe the path to code. This is step 2 after all local sum computing. This code runs simultaneously on all processors. So all processors run at the same time. Yeah. So path to code can describe the procedure of sum reduction. Okay, cyclonization. Cyclonization, what can we can't always avoid any shared memory. Avoid data races by synchronizing writing and reading to get deterministic behavior. This is analog of buying milk. Your fridge has no milk. You and your roommate will return from classes at some point and check the fridge. Whoever gets home first will check the fridge, go and buy milk and return. What if the other person gets back when the first person is buying milk? You have just bought twice as much milk as you need. It would help to have less. This is one example. Analog. Okay, lock. Cyclonization. We can use a lock to grant access to a region so that only one thread can operate at a time. We must need all processors to be able to access the lock. So use the location in shell memory as the lock. Processors read the lock and either wait or set lock and go into critical sections. This is some hash code. The first sentence is check log. The second sentence is set log. The last sentence is unset log. So you can see set log from set log to unset log. This is a critical section. Yeah, this is important section. This is some example. This is cyclonization with logs. This is log cyclonization. So this is thread 1, this is thread 2. Okay. Hardware cyclonization. The solution is atomic read or write. Read and write in single instruction. Common implementation is atomic swap or register from register to memory. Pair of instructions for link, read and write. Write fields in memory location has been tempered with after link read. RISC-V has variations of both, but for simplicity, we will focus on performance. Okay, this is some operations. This is memory orderings. This is RISC-V critical section. This is one example. Okay, we can see Openmp. Openmp API used for multi-threaded shared memory parallelism. We can see compiler directives, runtime library utils, environment variables. This is the 3 sections. Portable standard. You can see this is the characteristics. This is Openmp. So this is summary of Openmp 3.0. This is some resources. Openmp. Okay, this is Openmp specification. The Openmp language extensions have included 5 sections. You can see parallel control structures, work sharing, data environment, cyclonization, routing, runtime functions, environment variables. This is the 5 sections in Openmp. Shared memory model with explicit thread-based parallelism. Multiple threads in a shared memory environment. Explicit programming model with full programmer control over parallelization. Okay, this is Openmp in our class, our course. Openmp is built on top of C programming, so you don't have to learn a whole new programming language. You will not become experts at Openmp. The key ideas: shared vs private variables. Openmp practice for parallelism, work sharing, cyclonization. Openmp programming model. This is one image. Openmp programs begin as a single process and execute sequentially. Until the first parallel region of the track is encountered. Fork and join are 2 operations. Fork. One per thread then creates a team of parallel threads. Statements in program that are enclosed by the parallel region contract are executed in parallel among the various threads. When the team threads complete the statements in the parallel region contract, they synchronize and terminate, leaving only the master thread. Okay, Openmp extends C with Pragmas are a processor mechanism C provides for language extension. Good mechanism for Openmp. You can see compilers that don't recognize pragma, just ignore them. Okay, parallel pragma and slope. You can see this is one example. Variables declared outside pragma are shared. This is thread creation. We can define by Openmp number thread. This is one creation, one function. Environment variable. Set this variable to the maximum number of threads we want Openmp to use. We can usually equals the number of cores in the underlying hardware on which the program can run. So thread creation, the number of thread creation is less than the number of cores. We can't create more and more threads. We must limit the thread to the number of threads. If we cut or divide the process to many threads, the role to use is less useful. So the number of threads equals the number of cores. You can see usually equals the number of cores. Yeah. If the CPU has 4 cores, we usually divide one process to 4 threads. Yeah, this is some conditions. Okay, this is Openmp number of threads. This is some code, some use. This is hello world. Hello world is some programming in several programming courses. You can see this is hello world from thread. So printf, this is the output language. This is printf. This sentence can output PID. This sentence can output unthread. This is 2 variables. Okay, Openmp work sharing. We can see this is Openmp directives work sharing. These are defined within a parallel section. We can see the fork, the join, 1, 2, 3. We can see shared iterations of a loop across the thread. Each section is executed by a separate thread, serializes the execution of a thread. Okay. This is building block for loop. We can break for loop into chunks and allocate each to separate threads. We must have relatively simple shape for our Openmp aware compiler to be able to parallelize it. It is necessary for the runtime system to be able to determine how many of the loop iterations to assign to each thread. No permission exists from the loop alone. This is in general, don't jump outside of any programmer block. Okay, this is not important, so you can look. This is not. Okay, you can see the summary is we can take advantage of parallel programming in order to further improve our performance. We need to be careful of data races and solve them with cyclonization technicals. Among law, lets you measure speed up and determine how much of an effect you can possibly have. So this is thread level parallelism. You can see this is thread level. Parallel threads, multi-processing multi-thread is important. So you can see this section. Okay. This is lecture 23. You can see multi-threading issues and the cache coherency. This is 2 topics in lecture 23. Okay, we can see review of lecture 22. Decryption software is slow software. SIMD and MIMD only pass to higher performance. Multi-threading increases utilization. Multi-core, more processes. Openmp and simple parallel extension to C. Small, so easy to learn, but not very high level. It's easy to get into trouble. It's some characteristics of Openmp. Okay, this is Cyclonization in risk 5, and these are defined with a parallel section. This is parallel hello world. Parallel hello world. Okay, we can see this. There are 4 sections in lecture 23. Openmp directives, common Openmp pitfalls, multiprocessor cache coherency, and coherency per talk. Talk is MOESI. Okay, this is some calculation. Or this is one calculation. Matrix multiple or matrix multiplication. Yeah. A multiple B equals C. So you can see A can show by rows, B can show by columns. Yeah, we can select the rows from A and we can choose the column from B. The result is C. Yeah, this is the result. Okay, this is matrix multiply. This is the pass-through code. You can see from for loop, we can see I and J and K are 3 variables. Advantage is code simplicity. Disadvantage is blindly match through memory. This is the disadvantage. Okay, you can see this is naive. Naive is simple. Yeah, this is simple matrix multiply. This is matrix multiply in Openmp. We can see this. We can see outer loop, spread, cross, and thread. Liner loops inside a single thread. Why is there no risk here? You can see different threads only work on different lanes. Each thread works on writing to different rows, never reducing a single value, because every write is unique. Unique is very important. So matrix multiply can be wrong. This is the question: what if cache block size is more than n? You can see if the block size is more than n, we won't use last half of the block. Cache block, we can divide the first half and the last half. So we wouldn't be using all the data into blocks that were put into cache for matrix C and A. What about if cache block size is less than n? if the block size is less than n, we must pull it 2 blocks instead of 1. And you can see the catch block is less than this condition. So catch blocking, we can see this topic. Increase the number of catch can hit you get by using up as much of the catch block as possible. For an n multiple n matrix multiplication, instead of striving by the dimensions of the matrix, strive by the block size. When n is not perfect, divisible by the block size, chunk up data as much as possible into block sizes and handle the remainder as the tail case. You have already done this in the catch laboratory. I really tried to understand it. This is catch blocking. Okay, we can see cyclonization. This is cyclonization problem. Problem is data race with sum. Solution 1, we can see crude body of loop in critical section. New problem can produce. Code is now severe. Each thread must wait its turn to add to sum. Solution 2, separate sum for each thread combined as n. Okay, this is Openmp reduction. The reduction is specifies that one or more variables that are private to each thread are subject of reduction operation at end of parallel region. The operation is performed to the variables at the end of the parallel region. Okay, this is simple use of reduction. Okay. Openmp directives. We can see common Openmp pitfalls. We can't just throw pragma on everything and expect performance increase. We can see might not change speed much or break code. We must understand application and use wisely. Discussed here, we can see data dependencies, sharing issues, updating share values, parallel overhead. This is some Openmp pitfall. Data dependencies. We can see configure the following code. There are dependencies between loop iterations. Splitting this loop between threads does not guarantee the order execution. Out of order loop execution will result in undefined behavior. Okay, the rest of the content we can learn in Thursday. Yeah. Today, the current week is 15
weeks.
Yeah. So
আমাদের এই যে শেষ ক্লাস না, হ্যাঁ এই যে শেষ না 17 এটা আর 시조 지수
the laboratory course is to 16 weeks. So the laboratory week, the laboratory course has twice.
Yeah.
Yeah. Okay. See you Thursday.